This is the Amp Hour Podcast. Released September 25th, 2017. Episode 361. An interview with Ken Shirriff.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
And I'm Ken Shirriff with Radar.com.
Hey, Ken, thanks for
Ken.
joining us.
Glad to be here.
We are big fans of your work. I think I speak for all of our audience of like every time a new link comes up, we're like, oh yeah, this is gonna be good.
How long have you been doing? It's Righto.com, RIGHTO.com, which is your blog website. It's a good old-fashioned text blog with photos and whatnot. And how long have you been doing that?
I've been doing that a few years now.
Well, actually, I see 2008 is your first post. Let's have a look.
So I don't think it went back that far, but...
Yep, sorry to tell you, 2008.
Well, maybe better than a when is a why, too. I mean, that's probably an interesting question. Like, well, how'd you get into this whole thing?
So, I've just been interested in, reverse engineering old stuff, and if I do stuff and don't put it out on the web, it feels kind of pointless. I like to share what I'm doing, so I figured having a blog is the best way to do that. And it's interesting to find out what of my posts people like, which of my posts people ignore. It's really rewarding when I find a subject that I'm interested in and the outside world is interested in too.
You'll find an audience for anything, really. If you
but
post
die shots.
they will come.
Die shots get extra awesomeness,
right,
So the iPhone charger, that was my biggest popular post ever. People really seem to like Apple technology and finding out what's inside it.
Got it.
That's not surprising at all. They're just
the fanboys and also the electronics nerds like us. So yeah, it's the perfect storm.
Yeah, and then conflicts will break out with half the people saying I'm criticizing Apple too much and half the people saying I'm an Apple fanboy. So I'm just
you leave them alone.
Steve's my hero.
That's right.
Yeah.
Oh man.
Goodness.
So how did you start? I mean, so obviously you have a lot of die shots. You have what's your setup there? I mean, what's your gear like?
So it's actually not as complicated as you might expect. I have friends with surplus electron microscopes and everything, but I just got a microscope off eBay. The secret is it's a metallurgical microscope, so the light shines from above down through the lens rather than below with a biological microscope, and that's how it lights up the dye.
But to get good dye shots, you can't just put the camera on the dye because you don't get enough detail, do you? You'd have to take like photos and stitch them together.
So I usually stitch together say 30 photos, use software called Hugin. It's a little painful, but, it works pretty well to stitch them and, give a detailed die shot.
Right. One project on my to-do list is I've got one of these microscopes, metallurgical one, very nice, and it's great for die shots.
Spared no expense.
Yeah, spared no expense. And but what I want to do is attach motors to the stage on it, which is the XY thing that holds your wafer, and then automate the process where it like steps at X amount, in X direction, and then automates the camera to take a shot, and then takes moves it again, takes another shot, overlap in, and then auto stitch them together. I think that'd be a cool project. So, gonna have to find time for that one.
I just do it by hand, sitting there, turn the knob a bit, click, turn the knob a bit, click.
Click, yep.
So you just have to like keep track of, as you're going, like as you're stepping across, basically? Is that the simplicity of it?
Basically, it makes the stitching a little harder because, the photos are not all even. The only problem really happens if I like move a little too far and there's a gap in the middle of the die, and then I have to go back and fill in that spot.
Oh, yeah. Okay. And so, what about like what's the relative magnification level that like? So, if say someone listening wanted to go and start doing this thing as well, is it like a 100x lens? I to be honest, I'm pretty clueless about that kind of the glass that would be involved anyways.
So I tend to look at chips from the 1970s, so I don't need a whole lot of magnification.
Okay.
I don't have the number, but probably about 200x magnification.
Yeah, I'm.
So surplus market though is possible.
I find anywhere from times 50, times 100, or times 200 if you really want to get in close. Like I've got a times 400 lens, and it's just way too close. Like there's too many issues with doing that, and you don't need to unless you're looking at bleeding edge dyes. But as Ken said, yeah, most of them like older ones, which are probably the more interesting ones, perhaps. Yeah, you can do it with times 50.
Decipherable, right?
Yeah.
Yeah, sort of. Mid 1970s is the point where I can see everything with my microscope, and there's few enough transistors I can actually figure out what's going on. I'm not looking at i7s or anything here.
No,
that's a whole different world.
Right. Yep. Right. There's a lot of transistors there. That's about all I can tell you.
Actually, once you get closer, you have the limits of how close the optics are to the dye, and you've usually have to use like a special optical gel and things like that to put them in between the lens and the dye, and to help with the light transmission and things like that. And it gets really complicated the smaller you get. So yeah, you can't like if you're looking for like an Intel i7 dye or something, and you really want to see individual transistor detail, you're not going to buy a microscope off eBay and just whack it under there and be able to see that sort of stuff. So
yeah, my microscope has one lens like that where you need to put oil between the lens and the dye, but that's just too much magnification.
I said gel. Yeah.
What about the? I mean, so I'm looking at which one is this? I guess this is one of your latest posts, or maybe not. But the examining a vintage RAM chip, and so basically you got this high level chip, but this is the metal layer that we're looking at right now. Is that right? So
yeah, if I just pop the chip open, it was a ceramic chip, so I could just tap it with a chisel and it pops open.
Okay.
What you're seeing is the metal layer. You can figure out a lot from the metal layer, but it also hides a lot. What I've found is that you can get this stuff at art supply stores called Armor Etch, which is designed for etching patterns into glass. If you put a bit of that on the chip, it will dissolve the oxide layer, and then you can just use hydrochloric acid and dissolve the metal. And so you can dissolve out the metal and then see the silicon layer underneath.
Okay, so you will actually step down through each of these layers, and because it's a 70s process technology, it's not like 300 steps or anything crazy like that. Not 300 steps.
Yeah, it's basically one metal layer and then the silicon underneath.
Right, it's a two-step etching process. You use Armor Etch and then the hydrochloric acid.
Yeah.
That's interesting. I thought it was just the hydrochloric acid. Is that... Or is that to just decapsulate like your plastic chips and stuff like that?
No, to decapsulate the plastic, you typically need boiling sulfuric or nitric acid. Right. And that gets a little too hazardous for me, so I have my friends do that, and I just stick to the ceramic chips.
Smart.
So anyway, yeah, you need the Armor Etch typically because there's an oxide layer over the metal to protect it.
Got it.
And so if you just put the hydrochloric acid on, it will dissolve where the pads are and the metal is exposed, but it won't get the whole thing.
So is that oxide layer put on by the manufacturer after the dye is made, or just does it form?
No, it's a manufacturing step.
Right, okay. And that's to what? Actually protect the dye from moisture, impurities, or whatnot, or what?
Yeah, just moisture and other contamination.
Right.
Anything that gets in can change the semiconductor doping and mess everything up.
Got it. Interesting. So I'm going to have to try this.
So how are you usually picking? I mean, so you said 70s vintage is kind of good just because the relative size of parts and stuff. How else are you deciding which ones you want to start poking around with?
Well, it's a combination of chips that I think would be interesting. I opened up the 8008 because of its, historical interest as...
You killed an 8008.
Yeah.
You killed a poor innocent 8008, did you?
Sacrifice for science, Dave. Sacrifice for science.
Then I have people who recommend, you should really look at this chip. I've heard it's cool inside. or I'll come across a chip and figure, hey, might as well take a look. Friends will have old chips they want me to look at.
Mm-hmm. I guess this is probably the swap meet specials are coming out after this, huh?
We'll link in the one down below for the vintage RAM chip. I found this fascinating because Robert Baruch on Twitter actually posted the die shot, and you saw it and went, "Hey, that doesn't look like a RAM chip." And then you started to analyze this, and what did it turn out to be?
So, I'm friends with Robert, and I've given him a bunch of my old 7400 chips that are lying around. So, he's a cool guy to work with. He took these die photos, put them on Twitter, and then it just did not look right to me. So I dug into it, and it turned out to be a touch-tone dialing chip.
A touch-tone dialing chip. Why would somebody?
Wait, so they put it into a package labeled 74LS at 189.
Yeah,
that's weird.
I can't understand why that would be a good marketing technique.
Robert told me, a relatively obscure chip like that.
Is it so your RAM could dial home? Is that what it?
I mean, these fake SRAM chips. If you remember back in I think it was the early 2000s, late 90s, the cache SRAM scam was big, where 32K SRAM chips, which back then they didn't have the buffers. The buffer things built into the Intel microprocessors, right? The cache. They didn't have the cache built in like they do now. So they used external 32K SRAM chips, and they were very expensive. So someone figured out, hey, we can just relabel them. We can just get dead chips or blank chips, relabel them, and sell them as these real expensive SRAM chips, and no one will notice that their computer is 5% slower because the cache should just turn off, like it just wouldn't do anything. And your average punter wouldn't know. So there was a huge scam market for that sort of stuff. So, but...
anything to make a buck.
Yeah, but an old 74LS, series RAM chip, I don't get it.
Well, the funny thing is that Robert contacted the eBay seller and told him that this chip was not what it was advertised, and the seller told him that it must have been damaged during shipping. Got whacked hard enough to turn it into an entirely different chip.
Wow, it happens all the time. It happens to me regularly.
Yeah.
Make sure you use lots of bubble wrap.
I was going to say, ship me some lead next time, and I'll see if it turns into gold, right?
Damn, that static damage, it can do wonders, can't it?
Yeah, right.
Unbelievable. Right, now, another, the amount of stuff on your website is phenomenal, and the amount of different stuff you've got on there. I love this. You've done mining Bitcoins with pencil and paper. We are not worthy. We are not worthy.
Why? Also that, yeah.
Yeah, I got a lot of attention for my YouTube video on that. It was
you did a YouTube video as well. Oh, you have a YouTube channel too. Oh, well, I will. I will subscribe. What is your YouTube channel name?
Probably Ken Shirriff. Nothing too creative.
Got it.
I should.
We'll link it in.
Okay.
Yep. Got it. Oh, 656,000 views. Yeah, that one went viral.
Yeah, it was. I expected there'd be dozens of people interested in it. It turned out to be more popular.
That's great.
So anyway, it was one of these things where I was, studying how Bitcoin worked, diving into the details of the algorithms. And it just occurred to me, I wondered if you could actually do these algorithms by hand. And once I thought of this, it's like I couldn't let go of this idea, and I had to try it out.
Well, I got to do it now, right? Yeah.
And it turns out that the mining algorithm is just very simple bit operations repeated over and over. This is why it's possible to make ASIC chips that can mine so fast, because it's just a very simple algorithm. It's easy to build in hardware.
Is it easy to do in parallel? Is that the thing? Because you're doing all the... Right. So that's where the ASICs get their advantage, is they run in parallel instead of a instead of a sequential processor, like an Intel.
And because the algorithm is so simple, you can fit a whole lot of those in parallel on one chip.
Right. Yep.
So, I also went on to try Bitcoin mining on an old Xerox Alto mini computer. and found, only
Gold.
could get like 1.5 hashes a second out of that.
So it's that like just a little more than 3x your standard paper and pencil.
So,
rate?
yeah, better than paper and pencil, but it's still going to take way beyond the lifetime of the universe to do anything.
To actually mine 1 Bitcoin. Yeah.
Yeah. And then I tried using an old IBM 1401, which is a business computer that used punch cards in the 60s, and this was even worse.
What? Just because it wasn't as good as the Alto? Is that the idea? Or what?
Yeah, not as good as the Alto, somewhat better than doing it by hand. But it shows that they could have had Bitcoin in the 60s if they just thought of it.
Right.
Oh, that's brilliant.
Right. I'll pay you in 3 weeks when the transaction goes through. I make it 3 years actually.
Tell us about the Alto, because you've been restoring an Alto computer. I've always wanted to get one. Of course, they're rare as hen's teeth. There's one at the Powerhouse Museum here in Sydney, and they won't let me take it apart. Mongrels.
Also, a little bit of background, if you don't mind. Young guy here. I don't really know.
Whippersnappers. What's an Alto?
I don't know why it's important. I can tell it's a computer.
Tell us, Ken.
Yeah.
All right. So the Xerox Alto is one of these computers that just revolutionized everything. Pretty much everything you think of for the personal computer came along in the Alto. Xerox not commercially revolutionized though, because it wasn't a commercial success, right? Well, it actually wasn't a commercial product.
No. They didn't. Didn't they sell a few or something? Didn't they?
A few years later, they came out with the Star, which they sold as an office computer.
Right. Yep. That's what I'm thinking.
But the Alto itself was just for research. They made about 2,000 of them, gave a bunch of them to universities like Stanford Research Labs.
Yep.
So it was basically a mini fridge-sized computer. It had a bitmap display. It was basically the first machine that had a GUI interface built into it. They developed the optical mouse for it. They invented Ethernet for it. They invented the laser printer. They invented Smalltalk and most of modern object-oriented programming. Things like scroll bars, menus. All this came from the Alto. Famously, Steve Jobs took a visit to Xerox PARC in 1979, saw the Alto and other machines, and thought this was such a great thing, and it inspired the user interface for the Lisa and for the Macintosh. So basically, the Alto is
so a little important.
What made GUI systems, windowing systems, mice, all these things, networking. It all comes back to this computer.
And that brings up the almost invented the phrase "great artists steal," and that's what Jobs did. He was wowed by all this stuff, went straight back to Apple and changed everything, and went, here's our future. We need to do a GUI, we need a mouse, we need the whole works. And
yeah, but, there was a whole lot of changes between what the Alto had and what Apple did. So it wasn't just
yeah, for sure. But it was the idea. No, it was the concept. Pretty much so.
So anyway, Alan Kay, who was big name in computers, came up with sort of the vision for the personal computer decades ago. He's the person who was one of the key people working on the Alto. He gave an Alto to sorry, I lost my train there.
He gave an Alto to somebody.
Yeah. So anyway, Alan Kay gave an Alto to Y Combinator because he'd been doing some work with them. Y Combinator was looking for somebody to get this Alto running, so they contacted me.
Right.
I got in touch with a few people who'd been working on IBM 1401 restoration at the Computer History Museum in Mountain View. Some people who actually had the hardware skills to get this machine working. And so we put together a small team, mainly Mark Verdiel, Carl Clonch, Luca Severini. And so, we worked for a year in Mark's basement getting this Alto up and running. We now have it running. We can run a lot of the old software. we're now looking at old discs that have been lying around Xerox PARC to see what
nice.
treasures we can find on them.
Oh my!
So
wow.
what were what major hurdles were there getting actually restoring this thing to working, like getting it just
power
to boot
supplies.
up? Was it
Well,
was there dead logic? Was it just power supply stuff? Was it just trying to figure out how it worked because it was undocumented, or what?
Actually, there's a whole lot of documentation online. Alto has put on BitSavers pretty much all the documentation schematics you want.
Nice.
So that helped us a whole lot. But getting the system running, it was pretty much everything from the power supplies weren't working, so we had to replace some capacitors. The display wasn't working, we had to replace a couple parts in there. The CRT was so dim you could barely see it, and then that problem magically went away
Right.
after we left it on for a couple of weeks. We only found
The phosphorus has to just rephosphor, right? Is
some sort of contamination that
chemistry, right?
burned off.
Oh, nice.
So, then we discovered that the system wasn't actually a working system. It had the wrong disk controller card for the disk drive it had, so that just would not possibly work together. We discovered that the mouse wouldn't actually plug into the mouse connector. We discovered that one of the boards of the CPU was the wrong board, incompatible with the other ones.
Oh, no.
So we had to do some swapping of parts. I should mention that this is pre-microprocessor, so the CPU is 3 boards full of TTL parts.
Oh my god.
Brilliant.
So
Oh yeah, I'm looking at pictures now too. Yeah, so you posted about this as you went along too. So we'll definitely link that in as you're talking
sort of
about
our
this.
weekly updates on what we were doing to get it working. We only found one bad chip in the system, an inverter that went bad for some reason. We discovered that the disk we were
Bit rot.
the disk we were trying to boot off, someone had used it as a test disk and rewrote it with random bytes. So obviously that wasn't bootable. We had a lot of help from the Living Computer Museum in Seattle. They have a couple Altos they restored, so they were willing to send us a good disk cartridge, display tester, and extension boards to help us work with the logic analyzer. So we got a lot of help from them. Alto, who has some large collection of Alto parts, he could exchange our wrong disk board for the right disk board. So
Nice.
it's really there's a community of people who appear and solved a lot of our problems for us.
That's great. Wow, how many of these are there in the world? I mean, I guess that kind of matters too.
So they made 2,000 and there's fewer of them now. I know of probably
if there's more, we got to worry, right? I mean,
they're multiplying.
they're multiplying.
So it's when I started, I thought this was a super rare thing, and then all these people start coming out of the woodwork who have them
I got one.
in their garage. So
Wow.
I know of the order of like maybe 15 of them that are around.
Okay.
Maybe 5 of them that are running. But
Is there any there's no purple screws in there, are there? You said it's mostly a lot of 74, not even 74 series.
Purple
you said.
screws?
Purple screw. Purple screw.
No.
The one part you can't break if you lose it, it'll never work.
Never heard that
You know
phrase, but I understand.
Oh, no. Oh wow!
Well,
Look at
there
that!
you go.
I got one up on Dave finally.
I've never heard this
Oh,
phrase
yeah, so-
either.
There you
Oh
go.
yeah, the purple screw. It's the one part that is impossible to find, and if you lose it, you're screwed, and you. Yeah. My old coworker said I didn't come up with it.
So basically all the chips you can get if you order them. Replacement capacitors, we couldn't find exact replacements. Usually the modern ones are a little smaller, but they still work fine. It's the disk drive that we're really worried about, that if things break there, we're not going to be able to get new read-write heads.
That's a world of hurt. Yeah, exactly. If it's something wrong with the head, you'd be actually in there winding your own with a ferrite and some tiny, 1,000 micron wire or something, Like, nasty. But it all worked.
Yeah, it all worked. We have it running. We can run
Fantastic.
Smalltalk. We can run a bunch of old games. It's remarkable the number of games people wrote for the Alto.
Wow.
So what is Smalltalk? Sorry.
So Smalltalk is
Young
a
guy.
programming language. It's one of not the first object-oriented language, but very close to the first. The whole design patterns thing came out of Smalltalk. It's basically where the windowing system came from, where you can have a desktop with overlapping windows. It's an interesting language because you can change the code for the running system while the system is actually running. So
what could possibly go wrong?
So as a demo, I would have the windowing system going. I would click on the object browser to bring up the code for the scroll bar. I would change the background of the scroll bar from white to gray, and then all your scroll bars suddenly turn into gray while the system is still running. So
Nice.
It's an incredibly flexible programming environment. It's one where you can see exactly what's happening. The code is all, you can dive down and see it and modify it while it's running. It's kind of crazy.
And the Alto has its own language, right? BCPL.
Well,
What is that?
So that's not an Alto-specific language. It was actually developed on an IBM machine. It's basically a predecessor of C. It's kind of like C if you made the syntax go weird and then you got rid of all the types except for structs and ints.
Okay.
But a whole lot of the things you see in C, you can look at BCPL and see, that's where it came from. Everything from pointer arithmetic to the ternary operator.
Got it.
This is, yeah.
Chris is just scratching his head.
I know. My brain's like, so there was times before. See, I knew this, yes, but sorry. I mean, I never got into the vintage stuff like Dave did, obviously. I mean, but I know there's a lot of people out there like that. But it's an interesting hobby from the outside for me because it's like. Because sometimes there's hard to replace stuff. It's kind of relying, like you said, this isn't like relying on certain chips, but like I know there's people that chase like those synthesizer chips for like voice stuff, right? There's like certain chips that just aren't made anymore, and so it's an interesting intersection too with your interest in deconstructing chips and also restoring parts like that or a computer like this.
Yeah, so I recently opened up a 76477 sound chip, which is used in Space Invaders, among other things, and reverse engineered how that worked.
Sweet.
Nice. What's in that thing?
So it's an interesting chip because it's a combination of analog circuitry and digital circuitry. So it's not digital in the way modern synthesizer chips are. Most of it is analog and controlled by external resistors and capacitors. But the digital part is interesting because it's not TTL, it's IIL, integrated injection logic, which in the 70s was the hot new thing that was supposed to take over the world and all our microprocessors would be built out of it. It's like a super dense form of TTL, but it didn't catch on. CMOS took over the world, and now it's basically gone. But for a brief period there, it was the hot way to build chips. And when I say hot, I mean literally hot. The power consumption of a microprocessor built in integrated injection logic was so high that they couldn't use regular ceramic. They had to use a special beryllium ceramic to get the heat out.
Oh, beryllium.
And since beryllium's toxic, they'd have to stamp a warning label on the chip.
Yeah.
Wow.
Oh, that's great.
Is it just because it's current based, or just that it ran at high currents, or what?
Yeah, basically, CMOS, you don't have any static power usage, but integrated injection logic is more like TTL, that there's always current flowing, and the more stuff you cram on there, the more current you have.
Right, and if you're making it closer and closer together, as chips are wont to do, right?
Yeah.
Why did they go down that direction? Was it a speed thing, or was it what pushed them down that higher power route?
Well, it was. I think it was mainly a speed thing. That nowadays we think of CMOS as obviously the way to go, and TTL as this old thing. But it wasn't until late 70s, 80s that CMOS actually became faster than TTL, and finally.
That's right. Yeah.
Finally killed it off.
Is that because of on-chip capacitance started going down, or what?
Well, basically, CMOS, you could scale it much better. TTL, you have all these resistors on the chip, so it's really hard to scale it down. So once you could make CMOS small enough, it just sort of beat out on TTL.
Yeah. Because CMOS, for those who don't know, is just basically transistors. It's just FETs in there, and that's it. You don't need the resistance. You don't need pull-up resistors. You don't need anything else. It's not bipolar. It's just, if you look at the schematic, if you look at the internal structure of, say, a CMOS inverter, it's just the two. It's just the two transistors, the top and the bottom one. That's it. You feed the input to the gate and the output from the source or whatever it is, and that's it, basically. So yeah, so you can make it denser and denser because you only have to fabricate transistors, whereas things like resistors take up a physical large amount of die space. So that's how it works. Am I right?
Yep. Very good explanation. Don't have anything to add to that.
So Ken, going back to the Alto real quick. I mean, I'm kind of just scrolling through your different things here. I mean, what else did you guys run into? I mean, I'm looking at the various disk stuff. I mean, you actually did have problems with the disk or no?
So the disk drive itself, the biggest problem we had there is it has all these foam components for air filtering, and over the decades the foam sort of turned into sludge.
Oh yeah.
So we had to clean out all the foam. We used just some weather stripping and to replace it. But
computer so big you're shopping at Home Depot, is that right?
Yeah. So some of the parts in the Alto are not entirely authentic.
They would have used it if they had it. They would have used weather stripping too.
But it all works. But we had to get the crumbling mushy foam out of there because if any particles flew off and hit the disk surface, would end up with a disk crash, and that would be bad.
How much did those old disks store? We're talking 8-inch floppies, right?
No. These are hard disks. It's
hard disk. Oh, right. Okay.
It's a removable cartridge that holds 2.5 megabytes.
Wow, that was kicking ass back in the day. That was really state of the art. And like, what the hell would you need 2.5 megabytes for?
Well, actually, the 2.5 megabytes went quickly because the Alto had the graphics that had font files.
Graphics computer. That's right. Yep.
So people would end up swapping these cartridges kind of the way people did with floppies in later years.
Or zip drives.
So you'd put in your cartridge, boot up, you'd pull it out, put in another cartridge, store files on that, keep swapping them back and forth. You might have like a stack of cartridges on your desk.
Yep. Because things really changed when computers started to hold images and video just went orders of magnitude above. But when you start storing images and things like that, back in the days of when all your programs were just text and executables and things like that, you could fit a lot of programs on like a 360K 5.25-inch floppy, for example. You could fit, hundreds of programs and things like that because they're just all instructions. But when you start doing storing bitmap images and fonts and other graphical elements, that's when the explosion in the amount of memory needed took off.
Yeah. At the time they built the Alto, it was kind of insane to have a whole bitmapped image because it required so much RAM just to display the pixels. You'd end up using half of your RAM just for the screen. And a lot of programs, they would blank out half the screen so they could use that RAM for other stuff.
Use the RAM, yeah. How much RAM did the Alto have?
So it went up to 512 kilobytes.
Right, and how much of that was dedicated? So it didn't have a dedicated display RAM? It actually shared it, did it?
So basically,
what was the architecture?
It was a more complicated architecture than you'd expect. You could basically have any parts of memory that you want mapped from memory into the display. And so typically you would have like each line of text on the screen would be a separate block of memory. So to scroll, you wouldn't have to move the pixels around. You could just change pointers and change the blocks of memory you're using.
So you didn't have to have a continuous block pixel for pixel. Are you saying that you could store different stuff in different parts of memory and then just pull them out and assemble them on the screen.
Right.
Kind of, yeah, you could actually do that.
Yeah, the downside was that there was no display processor. It was actually the CPU that was doing this.
Right,
so
yeah.
every scan line, the CPU was basically interrupted, pulling pixels out of memory and sending them to display. So you could end up having like half of your CPU just used for putting pixels on the screen.
Right.
Wow.
Do you know of any other vintage computer that has that flexibility, in quote marks?
None that I can think of.
Actually, yeah, I don't know of another one either. Like usually they have a fixed display memory. Now it might share the main computer memory, but it's actually allocated bit for bit, pixel for pixel kind of thing. And then you have a display processor which takes that memory bit for bit and then maps it to the display. But this one, wow, that's incredibly powerful.
Ken, could you give us a little bit of context in terms of where, like, so first off, when was the time frame that this came out, and like what would have been its contemporaries in terms of other vintage computers?
Sorry, there was none.
So it came out in.
But good question.
It came out in March 1973. If you look at the microprocessor world, things like the 4004, 8008 had just come out. There was a lot happening in the mini computer world. You'd have your PDP machines. You'd have Data General mini computers. The Xerox Alto actually copied its instruction set from a Data General Nova mini computer. But as far as interacting with computers, there's most business computers were using punch cards and reels of magnetic tape. People would have some CRT terminals, and we're doing things with 80-column lines of text on the CRT.
Yeah. True terminal, right? Instead of a display kind of thing.
So doing things with a GUI, doing things with bitmap display, that was very, very much a revolution. The Xerox Alto is actually where they invented the WYSIWYG editor. So Butler Lampson and Charles Simoni made the first WYSIWYG editor on the Xerox Alto. Simoni then left Xerox, went to Microsoft, and started the Microsoft Word project. So there's a direct connection between the editor on the Xerox Alto and Microsoft Word.
Yeah. Wow. That's crazy. Wow.
Chris is blown away. But yeah, this was revolutionary. It changed everything.
No, of course, and I think that's important to know that. Yeah, I mean, just to have that historical context around, like, why... Well, maybe that's another question, though. Like, why... Was it just because Xerox was looking to do that next big thing?
No, they were a research group. That's the thing. So that's why they didn't commercialize this.
Yeah, as far as making it into a product, Xerox is famous for fumbling the future, as a book title puts it. They invented all this technology. They failed to capitalize on it. Xerox management tried to kill the laser printer project 3 times. It was only because the engineers could hide it away that it actually survived.
Oh, wow. Skunk working it because they had to, huh?
The Ethernet was invented there, but then the people from that team left and formed 3Com and commercialized the Ethernet there.
Ethernet, yep.
Yes, okay. Yep. So a little bit of money there, huh?
So basically Xerox management just totally did not see the reason you'd want to move computers in this direction. But as far as a research project, the team, their goals were to look 10 years into the future, what the personal computer was going to be. As far as that went, they really nailed it, because if you look at the Macintosh that came out in 1984, basically 11 years after the Alto, so it was really they hit that what's going to be there in 10 years. The Alto was way too expensive to be sold as a product. It probably was the equivalent of $100,000 per machine.
Oh, wow.
So it's like, let's just, spend whatever we can, see what we could do with this technology, and then we'll know what's going to happen 10 years from now. So it's an interesting question. What would happen if you did the same thing nowadays? Looked at what computers are going to be like 10 years from now, built one at a huge expense, built a bunch of these, had people write software for them, and basically designed, the computer of the future that way. And it seems like something nobody is doing these days.
Yeah, that's a good question because
No,
I wonder,
except
like,
in
I mean,
terms of AI, maybe.
yeah, maybe,
Because
but this is a hardware thing, right?
Hardware is commodity these days. It's like practically.
Well, so this is a reconfiguring of flexible logic blocks,
people
right?
are working
So like
on
chips,
quantum and stuff, maybe, but
sure. But I'm just saying that, like, so this is existing hardware that was taken and reconfigured in a novel way, right? I mean, I know that it's extremely novel. I'm sure
because it was all
underplay that.
7.4 series logic. Like there was nothing.
Right. But I'm saying that
they
if you do
didn't
that
design
these days,
custom ASICs.
you have to do it on silicon, and you probably have to do it in a smaller and smaller way. So it would have to be so revolutionary these days. It feels like maybe I'm just not able to think in a leap like this.
Or is it?
But it's interesting to think if you spent $50,000 to build a cell phone today, to look at the technology of the future, what would you what would you end up with?
Your name would be Andy Rubin, and you just you recently did that, right? that new cell phone, yeah.
Well, even there,
I haven't heard about
it doesn't
this new
seem like a
phone,
10-year
Tell us.
10-year future he's looking at. But
That's
you never
true.
know,
right? Yeah, that's a very good question, and I mean, I guess this is where we get to benefit from being a podcast. If anyone knows of this and has any pointers, we would love to hear some tips to what to look into, because I don't know, like, where do you even start to look for that? It feels like the other thing that's missing from that whole piece is, like, there are no Xerox PARCs these days. There are no Bell Labs these days.
Not in terms of overall general stuff. Like, there's lots of little groups working on specific things. Like I said, AI, quantum computers, other stuff. But nobody would, there's no one big group, even at a company like Google. Maybe you could argue someone like Google or something might be, have groups working on stuff like that. But it just takes so many disciplines to do. Whereas back then it was just... I'm not going to say easier, but it was, things were more ripe for the picking back then, I guess.
Well, I find it kind of amazing that in that time period, if you wanted to build a computer from scratch, it was not like a crazy project. It was just something you would sit down, spend a few months, and you'd do it. Prior to the Alto, the team wasn't allowed to buy the DEC machine they wanted, so they built their own server.
Yeah. You can't tell me what to do, Dad. I'll do it myself.
David, my cohort here, is sitting opposite me. He just pointed out the Google D-Wave quantum computer and stuff like that. There's people working on those sort of things. So I guess hardware-wise, you could say quantum computer is the thing that people are working on next. And software-wise would be the AI, and user interfaces. Well, there's, many companies working on, gesture interfaces and also, brain mapping interfaces. And there's lots of, different input methods and output methods, GUIs and actual display systems and stuff like that. So, but there's no one large group doing it all.
Well, let's come back to this podcast in 10 years and see how many of those things turned into the technology of the future.
See if we can buy a quantum computer on eBay, right?
Yeah, right. Yeah, or if Ken's fixing one up. That's the real question, right? So Ken, what happened? I mean, so you said you got through some of this stuff, you got up and running. Like where is the Alto now?
So we recently took it to the Vintage Computer Festival in Mountain View and showed it off to a bunch of people there, and that was a lot of fun. We showed people the old software, the text editor, the drawing programs, the games, Smalltalk. We have it up and running. We're showing it off to people. We haven't figured out what to do with it long term. I'm thinking maybe... I could put a web server on it, put it on the internet. But I don't think it would
have heat your house, right? Yeah. Oh yeah, you guys don't need heaters in California, so never mind. Well, you can always, you can do 1.5 blocks per second, like you said. You can mine some Bitcoin, right? Slowly.
Make my fortune that way.
Yeah.
Okay. Is it on the internet? I mean, so you said that these things had Ethernet. Is it on the internet? Does it even capable?
So unfortunately, the Ethernet is 3 megabit per second coaxial cable. So it's basically entirely incompatible with modern Ethernet. Fortunately, the Living Computer Museum in Seattle, the team there built a FPGA gateway so you can actually hook the Alto's Ethernet up to this, and it will talk to modern system. And so, you can now connect Altos over the internet. I can connect to Google and download a web page. I want to write some software so it could actually render, so you could actually browse the internet on your Alto.
So you have to write your own browser.
Yeah. Please, JavaScript programmers, have some mercy on Ken's computer here. he can't handle those 100 megabyte pages that you're creating these days.
Yeah, it's scary. There's a lot of websites where their homepage wouldn't fit in the entire memory of the Alto.
Right. That's insane.
Guilty.
Wow. Yeah. I mean, probably in the amp hour. I mean, we utilize stacks based on stacks, which we don't have any idea how to write. Yep. So we're just as guilty.
So on one of the old disk cartridges from Xerox PARC, we found a bunch of software for early experiments in voice over IP, basically.
No way.
Wow.
Ethernet telephony. They were doing software in BCPL so that they could send voice over the Ethernet. We're trying to figure out if we could make the necessary hardware so we could run this old software.
That's insane. They invented everything.
Right. There are no new ideas, people.
No. It all comes from Xerox.
Just new ways to charge your credit card for the same old ideas. Man, that is awesome.
I can't believe I don't know this, but was the PARC, the Xerox Palo Alto Research Center, was that publicly funded in some way?
No, it was funded by Xerox.
It was 100% Xerox funded.
So,
right.
At the time, Xerox had, pretty close to a monopoly in photocopiers. Every time you hit the copy button, Xerox would make their 10 cents. So they just had, more money than they knew what to do with.
Right.
So, they started this research center. It's a theory of mine that to have a good research center, you really need to have a monopoly to fund it. Because basic research isn't really profitable on its own. Look at Bell Labs. How much did they make off discovering the Big Bang? So
they made not. Yeah.
Wait a second. I don't know what you mean there. Sorry. The Big Bang.
Bell.
Wait, you mean did they have from the the microwave telescopes you're talking about?
Way back when Bell Labs discovered the Big Bang, when they were looking for why were they getting
cosmic background radiation is what we're talking about.
Okay. Okay. I was so confused for a second. I'm like, wait a second, did I miss my history class? Sorry. Okay.
So maybe that's a little too confusing there, but. but the point is that if you have a research lab funded by a monopoly, you can discover a whole lot of things even if they don't turn out to be profitable.
Yep. Oh yeah, if I was a squillionaire and owned Google or something, I would just live down in. I'd just set up a team and just live down there and just work on cool shit. Who cares if it made money? Doesn't matter.
Yeah. Speaking of other, maybe not monopolies, because this is a secondary brand, but you've also you did stuff with Sinclair's 1974 calculator hack. Can you tell us about that?
The Sinclair Scientific. It was a scientific calculator that was very cheaper compared to the HP's calculators. So it did really well in the marketplace. They used basically a Texas Instruments 4-function calculator chip, and somehow they managed to make this do scientific calculation, trigonometry functions. So I wondered, how did they manage to do this? I got die photos of the chip from somebody else. I could look at the die photo, read out what was in the ROM, basically figure out what the code it was that they were running, and determine how they managed to make this very primitive 4-function calculator chip magically do logarithms, tangents, and so forth.
And so when you say the 4-function chip,
it took a couple months on and off.
I was going to say, that's nuts.
So it turns out that they use some really clever algorithms for for doing these scientific functions, and also they didn't care at all about accuracy. You know,
It's only a calculator,
Right.
Hewlett Packard went to all this work to make their calculators
Yes.
accurate to the last digit. And then Sinclair, it's like, forget that. We're going to make a cheap calculator. It's, most of the digits are going to be mostly accurate most of the time, and
If you put scientific in quotes, I think it counts, right? You just scientific air quotes.
well, their goal was to be more accurate than a slide rule. So
right.
a few digits of accuracy would do it. One of my favorite parts of the calculator is that they didn't really have any space for ROM storage, so they printed constants like e and pi on the case of the calculator.
Yes.
If you want pi, you just read it off the case and type it in yourself.
Yeah, ink don't cost nothing. That's great.
That's
and
true.
so you went and so not only did you reverse engineer it, you also then you made a simulator,
A
which
little
is really
simulator.
cool.
It's very cool.
Yeah. So I built a simulator in JavaScript, so you can run it in your browser. Push the keys on the simulated calculator and step through the code and see exactly how it's doing its operations. And it's all based on decimal, so you can watch the digits as they shift back and forth.
It's great.
It's like multiplying. It's like basically doing repeated addition and shifting, and then for trigonometric functions, they're doing basically very small rotations over and over, which means the bigger the angle you put in, the slower the result. So,
oh wow!
And
these are actually I'm sorry, I started clicking the buttons and I got distracted there. So you can actually watch the custom application, like the actual. You click it and it actually inputs it does the full operation.
Yeah, you can see what the calculator would be doing internally.
Wow, that is so cool.
Damn.
And this is what you do in your free time, huh?
Yeah.
Okay, that is fantastic, man.
We have to ask, what is your day job?
Yeah.
So I worked at Google for about 12 years on a bunch of projects, everything from enterprise search to maps and location. Worked on Android before and after that was released. So currently I've decided to take a break, and so now I have much more time to devote to my random projects.
That's
Sweet.
awesome. Oh man. Well, what's your next conquest for reverse engineering? Other calculators in your future? Are you?
Well, I've got a collection of chips of various sorts that people want me to take a look at. So I'll probably open those up. I tend to get distracted easily, so I'm trying to keep those hidden away.
Right, open on a rainy day kind of thing.
So earlier in the year, I opened up a 8008 processor, did a bunch of photos of that, reverse engineered the circuitry by tediously drawing out every polygon. So I want to get that running in a simulator. So I've been talking to the Visual 6502 team. They did the amazing simulation of the 6502.
Brilliant. Yep.
That's actually what pulled me into trying to figure out how old chips work. When I saw the Visual 6502 webpage, it's like, wow, this is amazing, but I have no idea at all what's going on here. As a computer person, shouldn't I sort of understand how computers work? So I want to get the 8008 simulator working. It's run into a few timing problems, so I put it aside for a bit.
Have you got any plans to return to YouTube? Because you've basically released like 5 videos in 5 years or something on YouTube. Because you've got so much back material, I feel as though on your text blog, I feel as though you could just take that material and make YouTube videos.
Yeah, but Dave, he knows how the algorithm works, so he's
yeah, right. He can game the algorithm then and become a YouTube superstar.
He wrote the algorithm. Well, for all we know, we didn't ask. We don't want to know. We don't know. We don't want any secrets from Google.
Yeah, I'm not really big on videos. They take a whole lot of time to put together.
They do.
I'm more into blogging.
But they can reach a much bigger audience, though. You said right at the start that finding and reaching an audience was, a big kick, as all of us can understand.
Right, they'll all love to pretend to tell you they know what they're talking about, and tell you how you're wrong. So,
So one of the guys.
No comment section on your site, I noticed.
So one of the guys I do the Alto restoration with has a YouTube channel where he goes into great detail of how we're doing on the restoration, what's inside the Alto, and that's Curious Mark.
Right.
Curious Mark.
MARC. So you should check that out. So basically, he focuses on the videos, I focus on the blog, and we get all the
Got it. Okay.
everything covered.
Yep.
That's awesome. Did I see you have another calculator simulator too? A TI?
So that's basically the same chip that the Sinclair Scientific calculator uses. So I started by doing that one until I understood how the chip worked, and then I moved on to the Sinclair Scientific.
I see.
One nice thing about old Texas Instrument patents is they go into huge amounts of detail. They'll patent some trivial thing, but they'll have like pages and pages of entire schematics for the calculator chip, all the source code that the chip is running. So it's
Brilliant.
a huge trove of information going through their old patents, and that's how
awesome.
I figured out how to reverse engineer the calculator.
That's great.
Nice.
And like you're saying, like even to the source code, like just like the machine, the opcodes and stuff like that going into the chip.
Yeah.
Is that, wow.
So they'll have like flow charts and then the assembly code. So it's the patents were clearly written by engineers and not lawyers because they actually explain what's going on, how it works.
Yeah.
In plain English. And not rewritten in gobbledygook.
Oh, legalese. You
Yeah,
mean?
legalese.
I was gonna say probably not English, but
Well,
engineering.
Yeah.
Oh yeah, you linked to it too. 3934233. There you go. 50-page patent. Damn, that is crazy.
And at the end of the patent, what they're actually patenting is something they could have probably described in one page because it's a very small, obscure feature. But I guess the engineers wanted to get everything in there that they could, and I appreciate it.
Yeah.
I've looked at a lot of patents, and almost all of them are pretty much useless. But the Texas Instruments ones, they did a good job as far as informing people of what's going on.
Round of applause for the
Yeah.
for the TI nerds. Absolutely, that's great.
So what about generally reverse engineering? I mean, did you start out thinking that you were doing reverse engineering, or was it just like, I just want to see how this thing works?
So it's mainly just I wonder what's inside this. Let me see if I can figure it out. Mm-hmm. So I'd open up a charger, see what's inside it. It turns out that phone chargers are much more interesting inside than you'd expect. There's a huge variation in what's inside. A $2 charger on eBay.
Oh yeah,
it's like so simplified that they can sell it at this price. They cut out all the safety features, so it can kill you, but it's really cheap. Then on the other hand,
MOVs, who needs those?
Apple, it's just amazing. They've crammed every possible thing inside this tiny cube that they could. I would call it over-engineered, but it's impressive what they can put in there.
Yep.
So tell us some more about that. So yeah, this is one of your other top posts on your site as well. What is in one of these chargers? I mean, that was surprising.
So basically, a phone charger. It's a tiny switching power supply. It's like turning the power on and off tens of thousands of times a second to get the right voltage. At these high frequencies, they can use a very tiny transformer, that can fit inside that charger. This is why you can now get a cubic inch charger rather than the giant wall warts that people had in the 80s and 90s.
I've got a box full of those.
There's a chip inside that is controlling it, making sure that it is turning on at the right speed to get the right voltage out. Then there's a filtering stage to filter the power so it's nice and clean. The Apple charger, they've got extra safety features, your sensor in case it overheats, it will shut off. The MacBook charger, I was quite surprised to find it has a powerful 16-bit microprocessor inside, actually a microcontroller. I figured that it was roughly the same power as the original Macintosh inside your power supply.
Yeah.
Wow.
Basically, it's monitoring when you plug in your connector into your MacBook, so that it waits till you're solidly connected before it ramps up the power, and that way you won't accidentally short it out and get giant sparks. So if you get a fake MacBook power supply and stick a paper clip into the connector, you get quite impressive sparks. But with the real one, this processor is making sure that doesn't happen.
So it's doing like a handshake first and then saying, oh yeah, this is definitely connected, or how is it doing that?
Yeah, basically, it's this communication with your MacBook over how much current is being drawn, that it's like, basically, when you first plug it in, there's only a few microamps. Then the MacBook will apply just the right resistance to draw more current to tell the charger that it's connected. At that point, it will ramp up the power, and everything goes smoothly.
Oh, and this is like when the LED turns on in the MacBook little magnetic connector.
So, it turns out that that's actually an entirely different handshake. That the connector has its own little chip, and it has a serial protocol that it uses the middle pin of the connector to talk to the MacBook. It tells, so the connector itself is telling the MacBook what wattage the power supply is, and then the MacBook tells the connector which LED to turn on.
Chips inside a connector I want off this planet.
No way, man. This is good too, because if you drop it in a thing of water, well, I don't actually know. If you drop it in water, it still shorts out, or what?
So if you drop it in water, the microcontroller inside the power brick itself will detect things are bad and will immediately shut off.
Oh yeah, here we go. The DS2413 one wire. Yeah, so it's a Dallas part, the one wire protocol stuff.
It's
okay.
It does this serial connection over one wire, which is the middle pin of your connector.
Yeah, cool.
So one wire and ground. So it's more like two wires, but
right. Oh yeah. Well, that doesn't sound as sexy though when they say that, right? One wire, ground return, right?
But it actually gets both the power and the signal through that same wire. So that's that's where the one part comes in. Right. Yep. It draws current on the rail and then it tugs down on it, kind of thing.
Yep.
Yeah. Yeah. So what made you open this one up? I mean, just
I had read this book about Steve Jobs where he talked about how Apple had revolutionized power supplies for computers, and I thought, wow, that's amazing. And then I researched it and discovered no, they actually just used standard technology. But people told me that the Apple chargers were actually pretty cool inside, and I'm like, seriously, how cool can a charger be inside? So I opened them up, and it's like, wow, they actually did a lot in here.
And that's across. Is that just for the MacBook, or is it for other stuff too, like iPad, iPhone, stuff like that?
So the the MacBook chargers, those are the ones that have the powerful microcontroller, and then the iPad, iPhone chargers, those ones, there's less technology inside, but it's amazing just how they've managed to compress it down into like, a 1-inch cube.
Yeah. And I see. And then there's a picture here you show side by side with a counterfeit as well. So that's illustrative, I suppose, of how much stuff.
The counterfeits, they also fit down into this tiny cube, but they do that by removing all the safety requirements.
Yeah.
You're supposed to have certain distance between the high voltage and what comes out of the charger, and they're like, forget that.
Yeah, don't worry about that.
Most of the time it won't kill anyone.
Except when it does.
Right.
And that's okay. It's user's fault.
So I really don't recommend using the $2 chargers because first they're dangerous, and second they cut out most of the filtering, so the power they put out is just totally full of noise. The main symptom of this is your touch screen will stop working normally. Things will start jumping around, and that's because of noise coming out of your charger.
Right.
Yeah. That is buyer beware, I suppose, right?
Yeah, that's my public safety announcement for today.
Yeah, right. Well, before we cut off here, I'd like to kind of go way back. You also do. Let's see. You've also got a 555. You got a 7805. You got a 741. Anything that was surprising about those? I mean, these are all. People that are getting started in electronics obviously will know these parts. Well, anyone in electronics will know these parts. But what was surprising about these as you started to pull them apart? I mean,
and were they original ones from like the first year they came out?
No, they weren't. They weren't like the classics. Right. I mean, like they weren't the
Like Coke Classic. This is like the new Coke of parts, is it right?
Well, what surprised me most was that when you buy something like a 555 or a 741, it's like every manufacturer, they're totally different inside.
Yeah.
It's like I assumed that it would be like a standard part, and it's basically mostly standard behavior on the outside, but totally different on the inside.
Mm-hmm.
Oh, we were talking to Sprite about that a couple weeks ago. He was saying that for Wi-Fi chip. Oh, no, it wasn't.
Yes.
It was the serial. What's that serial part that every Arduino has on it?
The FT232.
Yeah, FTDI. That's right. Yeah. So they just do it however, and they just copy the behavior, but the silicon's different, right?
Yes, exactly. Because most people think, these chip cloning mobs in China actually clone the silicon. They don't, because they don't have access to the original masks. So actually cloning them is quite dead. It's easier just to design it your own from scratch and just copy the behavior.
So yeah, it was just a surprise to me that two chips that I thought would be identical inside turned out to be totally different. Sometimes it's not just the layout that's different; it's the circuitry is different. That's another thing that surprised me with the chargers. I've gotten a bunch of counterfeit chargers, counterfeit Apple chargers, and from the outside they all look identical, but inside they're all different.
Very different. Yeah.
It's like they aren't ripping off the other people's counterfeit designs; they're making their own counterfeit designs.
Well, they have a name to hold up for themselves. Come on, man.
But it does impress me just how much work they will go to eliminate one more component and save that extra penny.
Yep.
Well, it's simple math. Do that. Like if you're making 1 million of these, saving a cent on each one, it's serious money.
True. So are you seeing that as well in this? So are you saying that you also see those like efficiency, quote unquote efficiency tweaks to try and do the same thing on silicon, or is silicon just different because they, like Dave said, they don't have the masks, so they just do it differently?
Well, I've wondered about that. A chip like the 555, you can pretty much look at it under a microscope and draw out the mask.
They just trace it out. You mean?
Yeah. So why they make their own circuits? I assume they figure their engineers are better than the other engineers. They can do a better job.
Or maybe it's just faster than actually trying to re-tape out the mask.
It could be faster, but
I mean, they're probably not making much money on a 555. Let's be honest here.
But they're making enough money to make it worthwhile to do it, obviously.
So 555. But all these chips, you were surprised by some of these, the differences and such?
Yeah, that there's no sort of canonical 555 design or canonical 741 design. It's like they're just all over the place.
Yeah, and it looks like one of your notes on the 7805 thing is that it's even just between manufacturers themselves, right? So they all got to list different things, like 7805 is the standard 5-volt part, but even the manufacturers in the original, the older days, they were doing it different too, it seems.
Yeah. So it's like you think that a 7805, you know what you're getting, but it's just sort of a generic name.
Yeah, they don't do that as much as they used to, huh?
Sorry, in what way?
Oh, like you don't see you don't see ADI putting out a TPS whatever chip like TI does, right? They're not doubling up the names, like they used to, right?
Yeah, it seems like now they're using more unique names.
No, that's good. How did you start figuring out what? I mean, so like I went through these classes, I guess in school, and I always struggled with looking at dies and like the metal connection layers, all that stuff. How did you start figuring this stuff out and tracing it out? And did you have a background in that, or
no?
How
I'm
did
pretty
you
much
start
unqualified to do this.
Oh, okay.
I've have this collection of old books from the 1970s on microchip design and VLSI design. So I've basically just done a lot of reading and studying on my own. I look on Amazon, find these old books that describe what the technology was of that era and how they were building things. But chips like the 555, there's not a whole lot to them. Mm-hmm. It's pretty much a matter of just looking at it till you figure out, this is how they're building a transistor on this chip. Sketching out on paper where the transistors are, how they're connected, and then staring at it till it makes sense.
Got it.
I don't have strong background in analog circuitry, so I'll use LT Spice, the analog circuit simulator. If there's a circuit I don't understand, I'll put it into LT Spice, simulate it. It's like, oh, okay, now I see what it's doing.
That's good. Yep.
So it's it's a sort of hobby that pretty much anybody can get into if they have a lot of patience and you're willing to stare at a die for a long time.
Yeah. I would love to. It's just time investment. Try to learn that sort of stuff.
It's great though. It's really great.
I know.
I mean, like,
I'm envious.
and I guess my brain's starting to fall apart here, just like looking at all this content too. So I think the main thing that we should say is that we could talk all day, but like, there's so much good written content here that you really, I'm very impressed with how much you've documented, and as you were figuring it out, and as you reported on this stuff, it's really it's a great resource for all of us.
Well, thank you.
So what's next then? I mean, what have you done for us lately, Ken? Come on, man.
Well, I've been looking into some of the IBM punch card machines that were before the computer era. Going back to the early 1900s.
They were tabulators.
Tabulators, yes.
They were tabulators. None of this computer rubbish.
They were actually doing fairly complicated work. That have a card sorter that would sort cards, that have a tabulator that would run through a deck of cards and add up different fields, give you subtotals, give you totals, print accounting reports. And
the old
this is
Hollerith
sort of
machines. Are you doing Hollerith stuff?
So it's kind of this forgotten world. So I've been looking into that, and writing some articles about that.
Mm-hmm.
I also want to look into aerospace computers, which is another world that is pretty much ignored, even though there was a whole lot of innovation happening in there. In the 60s, 70s, people were building very powerful computers that were very small, and nobody pays attention these days to what was happening with aerospace.
Oh, like the Apollo guidance computer and stuff like that. Brilliant. Yeah. There's a great book on that for those who don't, like how they designed the Apollo guidance computer. Brilliant stuff.
But there's a whole world of computers that led up to the Apollo guidance computer.
Oh yeah, for sure.
Do you think? I mean, is that kind of stuff still floating around somewhere? I mean, or is it in a dumpster somewhere?
So
landfill.
Yeah, I assume these things were all destroyed as military secrets or something. So it's not something you can easily get your hands on. But there's things written about them. Some of these computers, they used these cool technologies. Back in the 60s, they gave cool names to their technologies like transflexors.
Yeah.
Nice.
So there's this aerospace computer that used basically core memories with two holes in them. They could use these for logic and called them transflexors. And I just think that's like, you don't get a name like that these days.
No, that's great. I'm going to have to call my next product something like that.
Oh man,
brilliant.
I guess if you go to the store and you ask for one, they'll know exactly what you're talking about, right? It's a branding exercise. Well, Ken, where can people find you online? I mean, I guess your site. Are you elsewhere online?
So, my site righto.com is where I put all my articles. I'm not really a Facebook person. I'm on Twitter regularly, so.
Yep, Facebook sucks. Stay off it. Twitter's the go.
I only post things on Twitter, every month or so. So, don't expect to see a lot of me there, but that's where you can find me.
People need to have the patience of someone staring at a die photo. And what is your Twitter handle?
It's just Ken Shirriff.
All right.
Sweet.
And I spelled Shirriff wrong many times last year when I was emailing you for Super Conference.
There are no E's in Shirriff.
Shirriff, is that right?
Yes, 2 I's, right. 2 R's, and 2 F's.
Right.
The 2 I's are not consecutive, though.
No, they're not.
Well,
awesome.
Ken,
thanks, mate.
Thank you so much for all this great content you put out online. It's awesome.
Yep.
Cool. Well, we hope to talk to you again soon as you take the next thing apart or put the next thing together.
Well, it's been great talking with you.
Thanks, mate. Catch you next time.
All right. Well, thank you.